Good afternoon, everybody. So welcome to this session, Climate, Heat and Air Quality Interaction Health. We will have 6 presentations. Each of them will have 12 minutes to present, and then around 3 minutes for questions. And Caroline, and I'm Hans-Oro, I'm in charge together with Caroline. Caro is following the online questions as well, and also showing you 1 minute and 2 minutes. First 2 minutes and then 1 minute. But let's start with Alexander Schneider, who will talk about small area analysis on heat effects on mortality and modification by air pollution in Europe. And the slides are on the road that you don't have to put up new presentation. You just stop when you use your slides.
Okay, many thanks, Hans. Good afternoon. I will start right away. So if you look at the global number of deaths that can be attributed to the different risk factors, you can easily see that among the top 10, there ranges air pollution and non-optimal temperature. And so far, they have often been investigated, but they have often been investigated isolated, so separately from each other. So I made a few arguments why it makes sense to look at them actually together or jointly. So on one hand, of course, temperature has an impact on air pollution via that air, for example, high temperature facilitates the formation of ground level ozone. But then there are also more mechanistic pathways that make an argument for joint effects between high temperature and air pollution. So, for example, if you imagine yourself in the summer and the warm months, you spend more time outside, and of course that increases your exposure to air pollution. Then also your thermoregulation is activated, and this increases your pulmonary ventilation, and this also then leads to increased intake of air pollutants. Then maybe if you are in heat, you are stressed by heat, and this heat stress actually reduces your ability to detoxify chemicals. And last but not least, there is hypothesized that there are common cellular pathways that are used by the effect of temperature on health and the effect of air pollution on health, like, for example, systemic inflammation. And so the aim of the exhaustion project was actually to look at the interaction of heat and air pollution and then health. And so we had the motto to debrief climate change. There has been already epidemiological evidence that heat effects are modified by air pollution. So, for example, there was a meta-analysis by Hu et al. In 2022. And also we ourselves published something in exhaustion using the MPC database. So we looked at 482 cities from 24 countries. And for example, these 2 publications already show that air pollution makes heat effects on mortality worse. But what was lacking is that, for example, these studies only use data from cities, so we don't know anything from rural areas. And we also don't know about why this effect modification might be spatially heterogeneous. So what factors are driving this heterogeneity actually? And so the objective of this analysis were to investigate the effect modification of PM and ozone on the association between heat and mortality, this time using small area data from 5 European countries. So with small area, I mean municipalities or lower layers or output areas or districts, depending on the country. And then also to explore whether certain land use factors or coastal typology could affect actually this effect modification pattern. And so, as I said, use data from 5 countries, so Norway, England, Wales, Germany, Italy, and the Attica region in Greece. And you can see that overall we had more than 6 million non-accidental deaths that we investigated from more than 43,000 small areas. for the exposure, we used air temperature data that was modeled, so with spatial temporal models, country-specific, in a resolution 1 by 1 kilometer, and the same is true for the air pollution data. So we had PM2.5 and ozone, we only had PM10 for Greece, and also on a 1 by 1 kilometer scale. And then we used these 1 by 1 kilometer grids and did some area weighted temperature and air pollution averages so that it fits to the small areas. And you can see one example here how it looks like for temperature and PM2.5 for the German small area. And then we had a two-stage analysis actually. So we looked only in the warm season, so May to September. We looked at non-accidental cardiovascular and respiratory mortality. We used Poisson regression models. And then for the interaction between temperature and air pollution, we used tensor smoother. And then we represent our heat effects as percent changes in mortality when the temperature increases from the 75th to the 99th percentile. And then we looked at the interaction with air pollution at certain percentiles of the city-specific or small area-specific air pollutant levels. So at the 5th, the 50th, and the 95th percentile of air pollution. And then we pooled that so that at the end we got country-wide effect estimates and then also overall estimates across the 5 European countries. And then, for the spatial heterogeneity part, we looked at certain area characteristics. So we used percentage of urbanized areas, green areas in square kilometer per 100,000 people, and then the coastal typology. And then we did a meta-regression of the heat effect estimates we had derived before at different air pollutant levels as the outcome variable, and then for the variable individual area characteristics. And so the results here. So this is first effect modification of heat by air pollution. So these are the heat effects at different air pollution levels, so low, medium, and high. And what you can see here overall across the 5 countries is that for PM, there's a clear indication that there are stronger heat effects at higher PM2.5 levels. And this was most significant, for example, in Germany. When you look at the right side for the ozone, there's also a kind of a suggestion of a gradual increase of the heat effect over the different ozone levels, but not so clear as for PM2.5. And it's also very clear that there were, for example, 2 countries where it's very strong, this increase, so for Germany and Italy. Then we did the same thing. So this was non-accidental mortality. Now this is the same for cardiovascular mortality. And what we see here is that we also see this increase for PM, but not as clear as before for the non-accidental mortality. But for some countries, it's still relatively clear. And then for ozone, overall, we actually don't see a big difference between the different ozone levels. But for certain countries, it was kind of clear. And then as a last outcome, we looked at respiratory mortality. Here, the effects are again rather similar to the non-accidental overall mortality, so more clear than for the cardiovascular disease mortality. So we see again this increase of respiratory mortality in relationship to heat, modified by the different air pollutant levels. And for ozone, it's interesting that there is not so much this gradual increase, but it's rather a difference of the very high ozone levels versus the rest, like the low and medium levels. And as I said, we were interested if this effect modification is actually spatially heterogeneous and which factors are driving the heterogeneity. And what we find are like not super clear effect, but you can see slight indications that, for example, this heat effect modification is more pronounced in rather or rather highly urbanized areas and areas with low greenness per person. And then for the cardiovascular mortality in non-coastal areas, it's a slightly stronger effect modification. And when we do the same for ozone, we also see similar indications like for the highly urbanized areas. We see more effect modification, but only for non-accidental mortality and cardiovascular mortality. And then also, again, the non-coastal areas pop up, but more for the just overall mortality. So to summarize, we found a clear effect modification of air pollution and in specific PM2.5 on the association between heat and non-accidental and respiratory mortality. So we had stronger heat effects on days with elevated air pollution levels. And when I say air pollution, I mean the particles. Whereas for ozone, this effect modification was not as clear, but we could also like detect it. And it's very specific to ozone that it seems to be just the days with very high ozone levels versus the rest. And then for the modification, it was more evident in highly urbanized areas, in areas with lower greenness, and in non-coastal areas. Many thanks.
Thank you, Rosis. There is already one question online. We start with this. How did you get heat maps, 1 kilometer resolution temperatures?
So that's a mixture of using data from satellites and data from measurement stations and combining that together in this 1 by 1 kilometer grid. So it's a longer procedure, of course, and I think I cannot explain that here in such shortness, but it's a hybrid model, more or less.
And probably that's already published somewhere as well.
Yes.
More questions? Yes.
Hi, I'm Julia from Cicero. Really nice presentation. Thanks a lot. I was wondering about the meta-regression because you have around, I think, 3 or 4 factors that you account for in the meta-regression analysis. And I was wondering if you've assessed a wide range of factors and then you picked these 3, or how did you decide to include these in the analysis? Thank you.
Yeah, we looked at a few more, but not many more actually, and so there was not a lot of decision to make. And I, of course, showed the ones that made a difference, but so we were mostly hypothesizing that like urbanicity makes a difference, of course, when you look at small areas. So it's not that we look at cities, but we look at these small areas, and then you expect, of course, that you see, for example, more heat effect modification in more urbanized areas, areas that are have a longer distance from the coast, because the coast, of course, makes a difference wind-wise. So we had some hypotheses first, what we would think would modify it. So we didn't try like thousands of variables because we don't want to do have chance findings. Thank you.
Sorry, just non-accidental deaths are all types of deaths except
the ones with an accident.
All mortality. It's all mortality, yeah?
It's all mortality, exactly. It's like more or less natural mortality.
And in all mortality, you also have cardiovascular and
of course. So that was not excluded and analyzed separately because, of course, non-accidental means everything, and then you go into more detail and like try to see if there's maybe a difference if you go more disease specific.
Thank you. I'm Abel. Maybe one thing that it's a nice presentation. First of all. One thing that I see from the conclusion part, and which I believe is a missed point, maybe the interaction of this temperature, ozone, and nitrogen dioxide. To some extent, there are some chemical transformations which makes the inflammatory insult more like effective. So have you considered that, at least in suggesting that there might be some for the chemists to look into this kind of interaction?
Yes, and we would have liked to also investigate NO2, which would be available for some of the countries, but was not available for all of them, and that's why we decided not to do it for NO2. But yes, I mean, ozone is related to NOx and NO2, of course, and then you need to consider this relationship, sure.
And the last question.
Just one question from my side. I would like to have your interpretation on the German data you showed us. It's well known and established that, for example, Northern Italy has a high amount of PM2.5. So that's not very surprising, but do you think it's traffic related, the heat relation you saw in your data?
So the PM2.5 has, of course, several sources, and we didn't look at source-specific PM2.5. So it's PM2.5 from industry mixed with traffic, mixed with whatever the particles in that size range come from. I mean, overall, of course, Germany was less polluted than Italy, but we had this whole range, right? I mean, we had Norway, which is less polluted than Germany. We had also Italy, we had the Attica region. So we had like a whole range of different types. And that's why we also chose for a low, medium, and high, we didn't choose a fixed level of pollution, but we use the percentiles for each country, because otherwise you run into the problem that a high level of Norway is a low level of Italy, for example, and then it's difficult to compare.
Thank you, Alexandra.
Sure.
And now change the microphone. I got the microphone. And we continue with Ola Thun, modeling past and future air pollution levels in Europe. And that's associated with mortality. Maybe but there was another one here. Now it should work. Now it should work. Yes.
Yes, I guess you can hear me. So, hello, my name is Ola Thun. I'm coming from Aarhus University, Denmark. Again, results from exhaustion project, but different work package after Alexandra, and I will do what she termed isolated effects. So I'm not talking about heat here, it's only air pollution, but we're working on it. I will maybe talking about past and future air pollution levels over Europe and associated premature mortality under different emission and climate scenarios. So there had been many introductions already this morning and also in the previous talk that air pollution is the highest environmental challenge and the highest risk in the factors affecting mortality. So anything that can mitigate the emissions of air pollution will be a health benefit, but also a cost benefit. So one motivation we had in the exhaustion project is that we expect to have increased heat waves or droughts in all globe, but also in Europe, both in terms of magnitude, but also the extent of these droughts. And this is some preliminary results from a paper from the exhaustion project, where we looked at different scenarios, and we can see that heat waves are predicted to increase at even faster rate compared to the historical rates, even under the most ambitious scenarios. And all regions across Europe are affected with this, but mainly the southern Europe turns out particularly vulnerable to this effect. The second motivation is that together with this heat and droughts, we expect to have increased wildfires, and we are already experiencing that, which is also a source of air pollution. Here again, I show some results from the exhaustion project, where we looked at different scenarios on how in the past and the future we will change wildland fires in different ecosystem types. And the bottom line is that you can see an expected increase in the future in the wildfires, which means more air pollution. So in exhaustion, we had three number of objectives, but for my talk, there was a main objective from work package 3, which is how the air pollutant levels over Europe will change in the future. And here we kind of use a multimodal approach to do historical and future projections of air pollution. Here I'll mainly focus on PM2.5 and ozone. And in work package 4, which deals with how premature mortality due to exposure to air pollutants will change, then we will apply a health impact assessment model using the concentration output that we got from the previous work package 3. So we use three regional models here, air pollution models or chemistry transport models. The DAY model from Denmark, SILAM from Finland, and then the weather research Wolfgang model that has been run by Cicero. And we did also a long climate simulation using the CSM model that was also done by Cicero. And then we kind of downscaled the climate and air pollution data from the CSM from course global model into more high resolution grid using these three models, where we used emissions from CMIP6, so what the recent IPCC has used. We have also further developed the ISFOL fires forecast model from FMI from Finland. So instead of using the emissions from CMIP6, we actually used our own emissions here. And then the SILAM model was also run in a global mode, where the regional models get the boundary and the initial conditions from. And then we used the EVA health impact assessment model. This is developed in my group in Denmark. This is a model based on the impact pathway chain. Here we use the model to calculate the all-cause mortality, but we can also calculate cost-specific mortality using different exposure response functions or risk ratios. And in exhaustion project, we also extended the model to also calculate mortality based on temperature extremes, but I won't be talking about this today. Here we used the relative fix from the recent WHO from 2021, which says that a risk of 8% per 1 microgram meter cube increase for PM. The model can calculate mortality, but also morbidity and costs associated to mortality and morbidity. But in this talk, I will only focus on mortality. So I won't spend much time on the model evaluation. This is just to show you the idea why we use multiple models, because as you can see, for both PM on the upper panel or ozone in the lower panel, if you rely on one model, you will be missing certain features, maybe overestimating, maybe underestimating. Of course, this is not news, but this was the reasoning behind where we tried to use 3 different models. And we compared them in this case for surface PM and ozone. We did the simulations both with the real meteorology, which is ERA 5 in this case, but also with the CSM climate which is in this case a free climate simulation. And you can see for ozone that the results are quite satisfactory. We have very low biases and high correlations. The PM is a different story. It's a bit worse, and there are many reasons that are already known for that, and we are not any different from those. But overall, we were satisfied with the results. And then we used to predict the different futures. In this case, I'm showing the results from the SSPs 126, which is the highly ambitious that we've seen this morning's talk that requires some net zero emissions. And we use 245, which is more or less what we promised currently. And then 370 which is if we do less than what we already promised. And then I'm showing you the multimodal means, not the individual models here. For ozone, we see a decrease, especially a high decrease if you are going very ambitious, and almost a 3% decrease by the end of the 2024-2050 period if we do what we plan to do now, and then a slight increase if we do less, which is consistent. For PM, the case is that we get a decrease in all different scenarios, up to 36-40%, depending on the area. And then, of course, the highest reductions are happening in the most ambitious scenario, which is SSP 126, that's shown with the red line. So if we look at these results, then in Europe, we can see that in all different scenarios, we get a decrease of PM, and in most cases for ozone. And this is just to show a special distribution of these changes. So the left-hand side is ozone, right-hand side is PM 2.5. And the main message is that we see most of the changes both in ozone, but also in PM 2.5 in the central to northern Europe, where there are the main emission areas. We also see some different changes in, for example, North Italy, where Po Valley is, which is highly polluted, the Benelux region. And these are more or less consistent within all models with a different, of course, magnitude. Then we also had a specific interest on the wildfires, but there will be a talk in this session. I think the next talk is about wildfires. Here I'm just showing you to make the point that the less we mitigate and the more we go in after the half of the century, so the map becomes more reddish, which means that we will be seeing more and more PM 2.5 due to wildland fires. And we use the EVA model to calculate the premature deaths. You see the ozone on the left-hand side and PM 2.5 in the right-hand side, and their distribution. So we see again a large kind of center, especially in 2.5 in the central to northern Europe, but also in northern Italy. And we really get very high numbers of premature deaths, around 800,000 in the year 2010. But you should bear in mind that this is the whole domain. This is not the EU numbers. This is numbers from Russia, North Africa, and other places. I've just received during lunch results, which I couldn't show here. When we only look at, we have an increasing and aging population, we still get much less reductions in mortality. There are other regions in the globe where this is just the opposite, like some Asian regions, even though they reduce a lot of their emissions because of the aging population, they get a net increase in their mortality. So this is at least according to these calculations, not the case in Europe. We also try to estimate the chemical contribution to mortality. Here I should tell that we give same weight to all different species. So each species doesn't have their own exposure response functions, but they are different. But they are the same response function they use. And overall, we see an increase in the organic carbon, both primary and secondary, attributed mortality. And this might be more important in the future because with the increased temperatures, we will probably see more secondary species. And we also see large decreases in sulfate attributed mortality because we are really reducing SO2. So the conclusion is that we know heat wave and duration and intensity plus wildland fires are expected to increase everywhere in the world, in Europe, which will lead to elevated air pollution levels. I also tried to show you that multimodal ensembles can provide maybe more reliable results compared to single models, or some indication of the uncertainty or model disagreement, which should be taken into account. We saw that the over Europe surface concentrations are generally going to decrease in all emission scenarios, but that depends which baseline you look at. So for certain baselines, you may have some slight different results, but overall, they doesn't change the conclusions. And we also saw that premature mortality decreases by up to almost 60% despite increasing aging population. So I'll stop here and thank you for your attention.
Questions? Yeah, Sorana.
Thank you. Thank you for a nice presentation. Did you try to use another effect estimate from lab studies that we also have proposed for EU to use a sensitivity analysis, acknowledging that this estimate 8% is likely underestimated for Europe?
Yes. So we also you made simulations with. This is what I said. I got results during lunchtime. We also got results from, for example, 6.2, the previous estimate from WHO report. So we got really much lower results, like 300 to 400,000, depending on the scenario. So, yeah.
But the one 1.12 from lab studies, the one that.
No.
No. Okay.
No.
I would hope you consider doing it.
Yeah.
As EU has done that also in their sensitivity analysis.
Yeah.
Thanks, Silas. I was wondering about the population data that you use, because I have actually two questions about that, because you have a global population in the future and you use 3 different SSPs, but do you use SSP specific population data as well, or do you use some different projections? And second, have you looked at subcategories in the population? So are you disaggregating it for age, sex, education, for example? Thank you.
So the first question is yes, they are SSP specific. So for 245, for example, it's the population projections for SSP 245. And in the model internally, we look at different age categories. Depending on the version, we can either do 5-year intervals, or we kind of separate them by children, adults, elderly, and stuff like that. But then the results are reported as the total. But we have also internally results that are per age category.
It would be interesting to look at the results from that.
Yeah, sure. But that's the only thing. We don't have other things like sex or other effects. Yeah.
Okay, thanks.
Thank you.
It's good.
Will be about wildfires.
Thanks.
Introduce this.
Yeah. Yes. So I'm Shorangshu, and I'm a senior researcher at CICERO Center for Climate Research. And this is a study that we did, and it was started by Mikhail and Risto before I joined CICERO, I think 1.5 years ago. And so this is on contribution on forest fires to ambient PM 2.5 and related excess deaths, present status, and future projections. Okay, so I'll not spend a lot of time on introduction. I think Ulas did introduced it, the topic to you, introduced the models, introduced the methodology, which is pretty much the same. And but I'll just say that this photo right over there, this was on a clear day taken over. This is the main building of University of California at Berkeley, and this was taken just after forest fire. And you can see how bad it gets. And this is because all the organics in the air, all the sulfur dioxide, the nitrogen dioxide that gets emitted into the air after intense spells of forest fires in the nearby mountain regions. So we all know climate change affects air pollution. There are multiple evidences of that, and we have been spending the entire morning for that. But the main effect of meteorological factors is on natural emissions and wildfires. And we have seen that over the past decade, there has been a surge in incidences of large and uncontrolled fires on all vegetated continents, and this has much of it can be attributed to warm springs, long dry summers, and drier vegetations, which fuel the increase in these fires. And wildfires may exacerbate or result in a range of health issues, including respiratory and cardiovascular endpoints. And there are studies which say that emissions from wildfires can be at least 10 times more toxic compared to emissions from other sources. Well, so again, the objective of this work is to quantify the impact of forest fires on air pollution exposure and human health for the present and future scenarios. I do not go much deeper into this. Ulas has explained about this. The fire emissions, we use the fire forecasting model that has the capability to produce fire emissions beyond the modest lifetime. We use anthropogenic emissions from the SEDS, which include industries, domestic, power generation, agricultural activities, and other sources. All of these were fed into the chemical transport model CLAM, and the resulting outputs at 2x2 degree horizontally, the resolution were used for global analysis, which Ulas said that drove the regional analysis. And we also had 20-kilometer results over Europe, which Ulas shared from 1990 to 2100. And these are under three scenarios, SSP 126, 245, and 370. And distinctly from Ulas, we use the GBD health impact assessment, which only takes a subset of the diseases that Ulas discussed. And we use the MR-BRT exposure response function, which is, again, the GBD changes their exposure response function with time, with the inclusion of more studies and more diseases coming to the forefront that are impacted by air pollution. Okay. So first, I'll talk about increasing importance of forest fires in Europe. So what you see in this figure are PM 2.5 exposures in bold lines for mainland over Europe, and thin bold lines for Western Europe, dotted lines for Central Europe, and dashed lines for Eastern Europe. Here is PM 2.5 exposure as a whole decreased by more than 50% over Europe. Whereas if you look at the red lines, which are forest fires, or contributions from forest fires, they are continuously increasing over much of Europe. More significantly in Eastern Europe as compared to Western Europe, but yes, it's increasing in Western Europe as well. So you might think that this is percentage contribution from forest fires, and because anthropogenic emissions are going down, the relative importance of forest fires are increasing, but that's part of the story. But the absolute exposure to forest fires has increased by more than 90% over most of that period. So this is excess deaths, and excess deaths from PM 2.5 exposure there in blue lines, and excess deaths from forest fire PM 2.5. So what we see is that excess deaths from PM 2.5 exposure has decreased when it was around 600,000 to about 2.5 or a bit more than 2,500,000 over Europe. So again, we use the GBD methods. So this is a bit different from the numbers that was presented. So what we estimate is that the excess deaths from forest fires have been increasing, and they increased more than 50% over Europe. And on the right, I have the fire mortality rates, which are excess deaths from forest fires per 1,000 deaths from PM2.5. And the blue dots are for 1990, and the brown dots are for 2020. And we see that the fire mortality rates have increased in all the European countries, more extensively in like in Ukraine and in Norway and in Russia, but less more so in many countries. But they have increased. Well, said that there are studies which say that forest fires can be at least 10 times more toxic as compared, or forest fire emissions can be at least 10 as compared to other sources of PM2.5, and that's because forest fires they emit a lot of organic carbons and they emit a lot of black carbons, and these have higher oxidative potential as compared to other compounds. So what we do, or what this figure shows, is that by considering forest fires to be equally toxic, and considering forest fires to be 10 times more toxic, which are the brown bars. So we find that by considering forest fire emissions to be 10 times more toxic, at least percent of total PM.5 that's in 2019 over Europe may be attributed to forest fires, and 25% of excess deaths in Eastern Europe, which is one quarter, may be associated with forest fires in 2019. Now, let's look at the global picture. So globally, forest fires were found to contribute less than 1% of the total excess deaths. But in sub-Saharan Africa, North and South America, their contribution is substantially higher, which is around 10 to 15%. So we find, globally, PM2.5 related excess deaths have been increasing. I mean, this is opposite to what we saw in Europe because of the successful air pollution policies we have in Europe. Whereas, air pollution or PM2.5 exposure has been increasing in India, in sub-Saharan Africa, and we see the total excess deaths from PM2.5 exposure to be increasing at a rapid rate globally. And forest fire-related excess deaths have also been increasing. And now let us see what the future holds. So I request you to put all your concentration on the right-hand side of this slide. So this is population-weighted PM2.5. And what we see is that the population-weighted PM2.5 is expected to increase under SSP 370 by at least 10 microgram per meter cube over most of, this is global numbers, whereas population-weighted PM2.5 globally is expected to decrease under SSP 126 and SSP 245. The decrease is more prominent in SSP 126 because of better air pollution control policies in SSP 126 as compared to 245. However, the contribution from fires, they're increasing rapidly under all these scenarios, especially under SSP 126 and 245. So here you see the excess deaths from PM2.5 exposure, which are solid lines. The dotted lines are contribution of fires. So you see that excess deaths from PM2.5 increases under SSP 370, under 245, and it almost remains at the same level as the present day under SSP 126. Just to be noted, we take population, demographic transition as well as changes in baseline disease rates into consideration, aging of the population as well. That's why we don't see a decrease, rapid decrease in excess deaths as we see for PM2.5. However, if you look at the dotted lines, the contribution of fires, the excess deaths from forest fires is projected to increase under all the scenarios. Now let us look at Western Europe and Central Europe. You see that excess deaths from PM2.5 exposure is expected to decrease under all the scenarios. However, the excess death from forest fires are expected to increase rapidly in both Western and Central Europe. So this is the spatial distribution, and if you look over here, which is the present day, we have high contribution from forest fires to excess deaths in in sub-Saharan Africa, in parts of in South America. However, if you look at the future, the future projections, forest fires are expected to be major sources in most of the developed parts of the world, in Scandinavia, in Northern America, and that is because of stricter air pollution control resulting in significantly lower contribution from anthropogenic sources. So what the forest fires are expected to do is that it's expected to jeopardize the goods of air pollution controls that are going to happen under these good policies, SSP 126. So now putting forest fires in light of other sources, you see that this is for the present, this is for 1990, 2000, and 2010. And then we have the future projections. The light colors are for SSP 126, medium colors are for SSP 245, and the dark colors are SSP 370. And we have the forest fires in dark brown. And we see that though, forest fires, the absolute contribution of forest fires to excess death is smaller in SSP 126 as compared to in SSP 370, which is a worse scenario in terms of temperature and air pollution, but there is a rapid decrease in anthropogenic contribution towards PM2.5 related excess deaths in SSP 126. Now, these are the conclusions. Forest fire is an important source contributing between 36,000 to 200,000 excess deaths per year. So why I mentioned this 200,000 is because, I have led a study a couple of years ago where we used different emission inventories, different models, and different health impact assessment methodology to find that forest fires contribute to about 200,000 excess deaths per year. But now we find 36,000 excess deaths. So the truth is somewhere in between, and there is no way we can validate it. We need more studies at the ground to validate such estimates. So what the figure that I have here is, it shows the transition in different factors like population age, population size, change in PM2.5, and baseline mortality rates towards the change in excess deaths. So you see that population age is always positive here. It's always resulting in the future decade. It's always going to be resulting in more excess deaths than now, just because of the changing dynamics in the population. Well, so forest fires are increasingly becoming an important source of PM2.5 related mortality in Europe, especially in Eastern and Central Europe, and it is expected to result in 7 times more deaths compared to present day in the last pentad under one of the least optimistic scenarios.
Questions? Yeah, on the back there is one.
Thank you very much. Very comprehensive presentation. Can you classify the cause of death in those excess deaths? And can you say project out how many are going to be related to chronic diseases and cancers beyond what you actually see and what you're reporting now?
Yes, we have a way to classify the cause of deaths, and but we can go only as far as the GBD method allows us to. So we have just included ischemic heart diseases, stroke, lung cancer, and diabetes, and COPD, and acute lower respiratory infection among children. they do interact, but we do not have the possibility to put numbers on them.
Thanks for the nice presentation. I was going to ask about this 10 times more toxicity. Is it only the emissions per se, or is it what the secondary particles also does after they are emitted?
It's both.
It's both?
Yes.
And do you wait to take that into account in the model, or you
no,
assume a constant?
Yeah, that's a very good question. So we have just considered forest fires to be more toxic and other sources to be less toxic in that way, keeping the total excess deaths the same. But we have also done, I mean, what you just asked, we did it in an earlier study where we put more weights on black carbon, put more weights on organic carbon, following earlier studies. For example, in the study that I led in 2022, we put more weights on black carbon and anthropogenic secondary organic aerosols and primary organic aerosols, considering they have higher oxidative potential as compared to other inorganic aerosols. And this was driven by a few studies that were carried out by Paul Serra Institute. Yeah. So we also have methodologies to do that. And yeah, we can discuss this here.
Thank you. Certainly you should discuss this. Thank you.
Yeah.
And next presenter should be from Ethiopia. Do you have Abel Kidane? No, it's like that. It's like that.
Like that, okay.
Yeah.
Okay, thank you very much. My name is Abel Kidane. I will present you this topic. It's one of the topics for my PhD. I'm on the 2 weeks of my PhD program. So my supervisors, they thought in this program, papers are not represented well from my continent. So why not? Why don't you try for the methodological framework so that everyone can see what's going on in Ethiopia? And you might find someone who can nullify your hypothesis and can come up with a new or more idea. So having said that, Ethiopia is a birthplace of coffee. So as coffee is an interesting and delicious beverage, for many Ethiopians, it's a source of exposure for indoor air pollution. It takes 3 hours of ceremony, the traditional ceremony, and we boil them on charcoal. So imagine what will be. So my study will focus partly on that and many other topics. So this is my content. So household air pollution, deforestation, and carbon dioxide emission are prevailing problems in Ethiopia. You can see more than 84% of the population relies on biomass of any type, like animal dung, wood, and the like. So, and this has caused like 3.9% of tree lost between 2000 and 2022. So this is a big problem, as you can see. They are interconnected at the same time. If you attempt to answer this question, this has to be answered as well. So there are a lot of sectors involved in this problem. And cooking using biomass in unimproved cook stove and poorly ventilated environment with the exposure, for instance, the PM 2.5 is around 400 ppm, the average in some of the rural areas. So this is what is going on in Ethiopia. What risk factor drive the most deaths and disability? As you can see, the most prevailing one is malnutrition, but the second one is air pollution. So especially in under 5 children, mortality is due to acute respiratory infection. So air pollution is the second leading factor for morbidity and mortality in Ethiopia. And you can see that 14% of the deaths, according to the GBD, and this disability adjusted life years of 10% of that is attributed to air pollution. And you can see the age standardized top 20 causes of death in Ethiopia. You can see that low respiratory infection is the top one. We have ischemic heart disease, chronic respiratory disease, and some of them, they are somewhat interlinked, are among the top 20 diseases in Ethiopia. So what is the research question? What is the level of household air pollution in Ethiopia is the first question, because you cannot deploy as many as possible instruments on the field to monitor, because that's not cost effective. At the same time, it demands cost and labor. So we need to come up with somewhat a smart approach. So we don't have that national representation of the data, where the GBD has some attempt with using satellite images and some papers published here and there, but they are not enough. And what is a burden? It's already answered by GBD, but there are some areas that needs to be more quantified with more precision. The important question, how much of the burden can be averted if exposure is reduced to 0 ceteris paribus? This is what the GBD, they look for the burden for specific point, static point, compared to the exposure reduced to 0 or 100% reduction, which is not achievable. So rather, looking for the avoidable burden is something what politicians wants to hear, and it is practical and good for planning. And what will be the second order impact of this estimation, and to present it to the people who are in the forest and the energy sector, they want to hear this one also. So my research question will answer these two prevailing questions. So this is a good from Murray. You can see that any intervention that is conducted at point time 0 with a lag effect, which we cannot avoid the impact in this skateboarding-like graph, but there is much to be avoided by reducing the exposure from 0% to 100%. As I told you, this is a theoretical and it's unachievable. So our experiment will rely in identifying which one is the cost-effective and the practical reduction. So by looking into this, we will also estimate the disease burden. Of course, simultaneously, if that disease is averted, we will also know how much of the carbon dioxide emitted will be reduced. At the same time, the number of trees will be saved. So I will come to the scenarios later. So this is a methodological framework. It looks like an abstract by itself, so full of color. So this is the entry point. I'm going to do some modeling for the exposure so that next time other scientists in my country can use this model by using proxy indicators to estimate the pollution level. So I have this information for 20 households, which we collected in a different project. So we're going to do an emission and exposure modeling for households. We identified more than 30 to 40 types of household models. So we're going to do that modeling first, then exposure will be estimated. But through this process, we're going to also see counterfactual exposure scenarios as a result of these proxy indicators. So the plausible is the most something that is practical and the feasible or cost-effective one. So if we transfer the traditional cook stove from what it is now to electricity, for instance, now we are building this huge dam on the Nile River, but there are competing interests. For instance, we have the industry is blossoming, so they demand also energy, but so the household and the industry has some competing interests. So we cannot go directly from the current scenario to full electrification. So we need to see for different feasible, cost-effective transitions. Once this is defined for different transitions, then this can be easily calculated. The science and the practice is already there. The health response function will be, it's more or less, it's generated from meta-analysis of different cohort studies from Europe, Africa, and developing countries. Then this risk will be characterized and quantified. So based on these feasible scenarios, I will calculate for the attributable, which is at point in time, and the averted burden by looking into future scenarios and generate this one. So the outcome at the end of the day will be on these two blocks. So the expected outcome is alternative intervention in policy scenarios over business as usual. So as I have shown you, the majority of the population relies on traditional stove and poorly ventilated houses. By incorporating this and going forward for different scenarios, almost 6 scenarios, which one is cost effective, which one is achievable in mid-term, long-term, and the like. The disease burden, these are the outcome variables that I will look into the exposure scenarios, the disease burden and the avertable. So most of the time we use the global burden of disease based on the disease burden, which is good. We don't have any option, but also we need to show for policymakers how much of those diseases can be reduced or averted if certain exposure scenarios are implemented, as we have seen for the ambient exposure previously in those presentations. And above all, these air pollution exposure models will be generated for different kinds of Ethiopian household structures, cook stove types. So this is much relies on programming and modeling scenarios. The significance of the study, the system framework can act as a facilitator to harness the planning and implementation of programs designed to realize climate resilient green economy and public health of the country. So we have climate mitigation programs and national policies, but those are not well crafted by looking into empirical evidence. So I hope I'll place a little role in that to show what are the concrete and practical scenarios for the program. So the project will encourage it will act as a springboard for the health sector, the housing sector, and the energy sector to come up with a common platform and plan together, because most of the time in my country, we have this problem of having poor multi-sectoral approach, and this study will create some favorable ground for that. Can provide direction for national socio-economic development, especially rural development. We have national planning institutions, but those institutions, they more or less tend to rely on common sense benchmark from desktop and other countries scenario. So this study will play some role in that process. I thank you.
Questions? Yes, please.
Thank you very much for your presentation and good luck with your PhD thesis as we are embarking on this journey. Just one comment from my side. As you have developed such a colorful framework already, I would really recommend just to add education to it, because when you look at neighboring countries, for example, what you see in Uganda, Uganda probably has a similar air quality as Ethiopia, also quite high in air pollution, and they are also fighting the same fight and battling with their charcoal. But they have some of the households, not all of them, have electrical places where they could cook. And they still use the charcoal because they do it for traditional reasons and they're used to it. So in a way, it's really important to educate the people why they shouldn't use it. And I definitely would also embark on education, not only of policymakers, but also of the end users.
Okay.
Somebody else? Yes.
Ninad Bondre, thanks for this interesting framework. My question is a bit related to hers, but in terms of, have you looked at learning from other countries with a similar socio-economic profile? Has this sort of stuff been done there?
Okay. I think, yeah, my framework, you're right, more or less focus on the hardware, but the software is also important. So we have the best primary healthcare system in Africa in general. It's one of the best, but now it's suffering to some extent due to the ongoing civil war, I can say. Households, like for every household, there is an assigned health extension worker, who teaches by going there every day or every 2 weeks to have a well-ventilated household and cooking platform. That information is being provided for the past 2 decades, if I'm not mistaken. But those programs are not supplemented with this kind of study. But I don't know if I add this human or software part to this model, it will burst out and might not be something that I can handle. But your point has critical importance to this kind of. So I think I will add to the ongoing intervention or primary health intervention program of my country. Yes, there are experience in India, the way they integrated this primary health care with this kind of transitions is one good experience. Also, Uganda and Rwanda, Kenya, the neighboring countries, they have the similar setup, but a different phenomena. So I'm looking into those experiences as well. Thank you for the questions.
Thank you for this.
Thank you.
And now we move to California from Ethiopia.
So hello, I'm Sandy Eckel. I'm joining you from Los Angeles at the University of Southern California, and I'm very excited to be here. I do want to mention that I am part of a larger team whose names are listed here, and I'm very happy to be here with you today. I do have to give a conflict of interest disclosure. The PI of this project, Erica Garcia, has some personal investments in automobile manufacturer companies that were pre-existing to this project, and I actually have a spouse who works in emissions testing at a car manufacturer. And so these conflict of interests are managed by our university and include independent review of our data collection and analysis, and none of the other authors have any conflicts. So the theme of my talk today is really about mitigation co-benefits, as we've been talking about earlier this morning. And as we know, the electrification of the transportation sector is an important climate change mitigation strategy. In the long term, we expect that this will reduce greenhouse gas emissions. And in the short term, there's these interesting possibility of co-benefits for public health. So of course, these co-benefits are thought to come about because of the idea of if we reduce tailpipe-related combustion sources, these are a major source of air pollution, such as PM2.5 and nitrogen dioxide. And of course, traffic-related air pollution. There's a large body of evidence that traffic-related air pollution is related to adverse health outcomes. But one thing to keep in mind is that much of the research in this area has been about projected health impacts of the transition to electric vehicles. So for example, in June, the American Lung Association came out with a report where they, under the assumptions of 100% transition to zero-emission vehicles and electricity generation that is non-combustion sources by 2035, in that case, the national cumulative benefit for the US by 2050 would be more than $900 billion in public health benefits coming not only from fewer premature deaths and fewer asthma attacks, as well as fewer lost work days. But one of the issues with this is that these are all projected benefits rather than with real world data. So I'm coming to you from California, and this is with the caveat that this is focused on the US, and in the US, California is a leader in EV adoption. You can see here that in 2022, of the number of EVs by state, California was by far the leader. And you can also see the trends in EV adoption here over time, really picking up starting from 2010. And so my colleague Erica Garcia and I, a year or two ago when I was in sabbatical, started asking this question, can we start to actually see the public health co-benefits of electric vehicle adoption in California? And so we're focused actually, the time period that we're looking at in our data is from 2013 to 2019. We cut off the data obviously before the pandemic because that would lead to a lot of complexities in our analysis. And so we were asking the question, can we start to look at increasing numbers of electric vehicles and see if there are impacts on NO2 air pollution, as well as asthma or emergency department visit rates? Now, when we're conducting this analysis, we're also very importantly thinking about the issue of equity. Are the co-benefits that are being experienced, are they going to be equitably distributed? So here are some maps showing the PM2. This is a zoom in of the Los Angeles area, if you're not familiar. So you can see that here is an example of the PM2.5 burden and the asthma burden overlaid on the Los Angeles area. And you can see that the same neighborhoods that have higher burdens of PM and asthma also have lower EV penetration. And so we are concerned that the underserved communities who have the most to gain from the transition to electric vehicles may also be not experiencing that transition yet. And so I'll keep this in mind as I'm talking about the data today. So basically the work that we did here was a creative use of all publicly available data. We were looking from 2013 to 2019. Our primary exposure variable, if you will, is the number of zero emission vehicles. And then ZEV is a technical term, if you're not familiar. It includes both battery electric, plug-in hybrid, as well as hydrogen fuel cell cars. And so we're looking at the number of ZEVs registered in each zip code over each year during this time period. We also are looking at measured NO2 air pollution at EPA monitors. You'll note that we used measured air pollution because we were a little bit concerned that there are many models of air pollution exposure, but we were worried that they might not fully capture the transitioning transportation landscape. So we relied only on measured NO2 air pollution. And so the EPA monitors, there's 107 stations in 95 zip codes. So we had to reduce the number of zip codes we were looking at by using these EPA monitored values. We focused on NO2 air pollution because it is a product of combustion related sources. We really wanted to focus on tailpipe related emissions. We also, our health outcome that we looked at was asthma related emergency department visits. These were also publicly available. We had data on more than 1,200 zip codes in California longitudinally, and these were, when they were made publicly available, they were already age adjusted. And finally, we looked at population characteristics from the American Community Survey, which is related to the US Census, to get information about population size in the zip codes, as well as educational attainment. This educational variable that we used was the percent of the population over 25 who had a bachelor's degree or higher. We acknowledge that we are using education as a marker of socioeconomic status that represents the structural and financial barriers to education rather than the lack of education itself. Okay, so again, in terms of our data analysis, we were looking from 2013 to 2018, and what's really crucial about our analysis is that we're looking within California zip codes. Within a zip code over time was the changing number of zero-emission vehicles related to changes in NO2 air pollution or changes in respiratory. The analysis that we used were linear mixed effects models where we adjusted for educational attainment as a proxy for socioeconomic status, and we also adjusted for calendar year as a proxy for secular trends, and we included zip code level random effects. And so here are our results. So first of all, we're looking at the number of zero-emission vehicles per 1,000 population as a function of time. And you'll notice striking increases in the number of zero-emission vehicles. And we have color-coded this by the percent college education in each zip code. And you'll notice a striking gradient here as well, where the zip codes that had higher levels of education have higher adoption of zero-emission vehicles. Zip codes with lower education are lagging behind in that transition. And so this is, importantly, I wanted to draw attention, this is what we term the adoption gap, where we're really concerned about the equity issues here in this transition. Then we have a plot looking at trends in annual average NO2 by site. You notice there's a lot fewer lines here because we're restricting our analysis just to the EPA monitoring sites within about 100 zip codes. And then you can also see trends in asthma ED visits. You'll notice there's a lot of variability across the zip codes, again, with some striking gradients by socioeconomic status. And so here's some of our preliminary results. We're looking at NO2 air pollution and zero-emission vehicles. This is an exploratory plot that we made looking at the 7-year change in NO2 versus the 7-year change in zero-emission vehicles. You see a suggestion of a negative association, as you would expect. And we estimated that within the zip code, if you saw an increase of 20 zero-emission vehicles per 1,000 population, we estimated that there was a negative 0.41 ppb change in annual average NO2. You'll notice the confidence interval is wide and it does cover 0, and it was not statistically significant. It's important to acknowledge that the power was limited in this analysis. We restricted down to the 95 zip codes that did have EPA monitors. And we also noticed that the siting of the EPA monitors tended to be in zip codes that hadn't yet really experienced that transition to zero-emission vehicles. And then in terms of the health analysis, we saw striking evidence that increases in zero-emission vehicles related to improvements in asthma-related ED visits. So per 20 ZEV increase per 1,000 population, we saw a 3.2% decrease in annual average asthma ED visit rates. This was strongly significant. Again, this analysis used the full set of zip codes that were available to us, and these results were robust to a number of sensitivity analyses. So some of the strengths and limitations of our analysis, we were using the number of registered zero-emission vehicles as a crude proxy for the local operation of zero-emission vehicles. An advantage of this metric is that it does vary temporally and spatially, that allowed for that crucial aspect of our analysis to be looking within zip code over time. Another feature to mention is that our zero-emission vehicle definition, it's a technical definition, but it does include plug-in hybrids, which potentially could be operating off of fossil fuels as well. Another caveat is that these data were available for light-duty zero-emission vehicles. I'm really excited about the transition to medium and heavy-duty vehicles, but there's not that many on the roads yet, so you really can't do this kind of analysis yet with the heavy to medium-duty, but those potentially will have big impacts in our local communities. We were also focused in our analysis on these local impacts at the zip code level. We were not considering the whole life cycle of zero-emission vehicles. We weren't considering the production of batteries, the recycling of batteries, or the electricity generation as well. And finally, it's really important to mention that this idea of electrifying the transportation sector is one hard to solution, we also obviously need to look at mode shift to healthy and active transport. So the key takeaways for this study are that this is some of the first data that at least I've seen on real-world evidence supporting the co-benefits of the ZEV transition. We were using observational data during a natural experiment of the early phase ZEV transition in California. And our results were that we found robust evidence for within zip code increases in ZEV adoption was associated with reductions in asthma ED visit rates. For the NO2 results, they were in the hypothesized direction, but not statistically significant. And in general, we found these results to be quite remarkable given how low the EV adoption rates were in California during our study period. But we did see this adoption gap, which is a point of concern that's threatening the equitable distribution of these co-benefits. The underserved communities, they are disproportionately burdened with higher health-related burdens, but these are the communities where the effects would be the biggest if we were able to achieve transition in terms of ZEVs. So we're hoping that this can inform future policies for a just and equitable transition to an electrified transportation sector, both to mitigate climate change and to realize environmental and health co-benefits for all. And then my final slide here on what's next. So we were able to leverage this pilot data that we've published into some NIH-funded research by my colleague, Erica Garcia, earlier this year. And so we are embarking on a project that is a community academic partnership with the SELA Collaborative as our major collaborator. They are the Southeast Los Angeles organization that is a group of communities. And you can see that these, if you look at the number of zero-emission vehicles in all of California in pink, and the SELA Collaborative represents communities here in blue. So we just 2 weeks ago, we had an advisory council meeting with leaders from these communities. We're going to be engaging in focus groups to really understand the opinions of people in these communities about this transition.